Okay, so this is question 7 from IA2 for specialists. This is a projectile motion question, and projectile motion is covered in chapter 4 of the textbook. So a ball is projected from ground level at an initial speed of 30 meters per second at an angle of 36 degrees above the horizontal. And we're going to use a model to determine whether the ball will clear a 10-meter high vertical wall that is 70 meters horizontally away from the point of projection. So the first thing that I've done is highlighted our important information, which we are eventually going to use in order to develop a solution. I've also gone ahead and just sketched a vector plane. This is very poorly drawn, but this is going to help us develop our solution. So I've drawn in from an initial point projection, which we're going to assume is the origin. The ball is projected at an angle of 36 degrees, and 70 meters away from this initial point of projection, there is a 10-meter high vertical wall. So now we need to develop a solution to determine whether the ball is going to clear this height here. So one of the first things that we need to know in order to solve this is that the only force acting on the projectile is the weight force, which is represented by our vector g, negative g, so that's gravity, j. Now the reason that this is negative is because it's a weight force, which means it's acting downwards on the plane, yeah? Okay, so this is also represented by our acceleration vector. And if we remember how an acceleration vector is represented, it's represented by 2 dots above our rt. So that'll be equal to negative g, j. That's our acceleration vector, and I'll just write that in brackets over here. Okay, so that's our acceleration vector. Now we need to integrate to get our velocity vector. So our velocity vector is going to be represented by negative g, t, j plus c. Just remember, this is still negative because it's acting downwards on the plane, and of course we've got our constant. Always remember to add your constants at the end when you integrate. So that's our velocity. Okay, and we're going to call this constant 1 because we're going to end up with other constants later. So that's our velocity vector. Now we need to use some of the information that we are given up here in order to actually develop a solution, okay? So what we're going to now write is our initial velocity vector. And our initial velocity vector occurs when t equals 0. And we're given when t equals 0, the initial speed is 30 meters per second. So v is equal to 30. So now we can use this information to develop an expression for our initial velocity. Okay. So this is still a velocity vector, so it's still going to be represented by 1 dot above the r. T is going to be equal to 0, and this is represented by v cos theta I, which is our horizontal component, plus v sine theta j, which is our vertical component. Now this is just a formula that you might have to remember because this is on the formula sheet from memory, but it's a pretty simple formula to remember because you should be applying this in other areas of vector calculus anyway. So now that we've got our initial velocity, so because this is initial velocity, this is when t is equal to 0. And we know that if t is equal to 0, then this must be our constant term up here. So c1, which is our constant, is equal to this. So therefore, we're just going to plug this in. Okay, so we're just going to plug this in to our velocity vector. So don't get confused between initial velocity and velocity.
Attention Year 10 students to go to the gym for parade. That's all Year 10 students to go to the gym for parade.
Okay, so once we substitute our initial velocity vector as our constant into our velocity vector, we're going to get negative, why is it doing? Okay, so we're going to get negative g tj, which is one of our vertical components, plus our constant, which is v cos theta I, plus v sine theta j. And now what we can do is we can add our like terms, because we do have like terms in this expression. And that is that we have a vertical component here, which is our weight force, and then also this vertical component here. So we can write this out with our like terms. And that's going to give us RT is equal to V cos theta I plus, in brackets, V sine theta minus gravity T, and that's our vertical component. Okay, now once we have that, we are going to integrate this again to get our position vector. So our position vector is just represented by RT. And once we integrate this position vector, we are going to get V cos theta Ti, which is going to be our horizontal component, plus, now remember when we integrate, we have to integrate everything in this bracket here, and we have two separate terms. So if we do this term first, we're going to end up with V sine theta T minus half G T squared, and that's going to be our vertical component. Okay, so basically now what we can do is we can let our V equals 30 because that's our initial velocity given, and we can substitute in our angle that we're also given as well. I'm just going to scroll down here. So we've got our position vector is equal to 30 cos 36 degrees T plus 30 sine 36 degrees T plus a half GT squared J. Also remember as well in this position vector we've got a second constant because we have integrated. So this will carry forward as well once we substitute these values back in. But now what we want to do is obviously we want to get rid of the constant. So how can we do that? Well, usually what we do is we'd let our expression equal 0 and time equal 0. And we're going to get that our second constant is equal to 0 anyway. So basically our position vector will just be this minus this constant over here. Okay, so now that we've done that, we actually have an expression for our horizontal component and for our vertical component. Now, if we see what we're given in the question, we are given a horizontal component, which is our 70 meters. So the first thing that we're going to do is we're going to equate those components, yeah? So we've got 70I is equal to I, because it's our horizontal component, is equal to 30 cos 36 degrees Ti. Now these i's are going to end up cancelling out anyway. So these I values are going to end up cancelling out anyway because we're equating the components. So what we're going to end up having is 70 is equal to 30 cos 36 degrees T. So now we can carry this over and under and we can solve for T. So we'll have T is equal to 70 over 30 cos 36 degrees. And once we put that in our calculator, we should get that T is equal to 2.88, and that is to 2 decimal places. Okay, so now once we have that value, we're going to let T in our vertical component. Okay, and here that means we can solve for our height, yeah? So if we've got our vertical component, our vertical component is equal to, so we're solving for the height, so our height is equal to 30 sine 36 degrees T plus a half gt squared. So now we can let g equal 9.8 as well. So our height is equal to 30 sine 36 degrees, substituting our value of t, which is 2.88, plus half, and then what our gravity is equal to, so that's 9.8. Remember, that's also on the formula sheet as well. 2.88 squared. Okay, so now that we've got this, we can put this all in a calculator because this IA2 exam is tech active. And then we should get our value of 10.14, which is to 2 decimal places. Okay, so let's go back to what the question is asking us. So the question is asking us whether this ball is going to clear a 10-meter high vertical wall. And because we found that the height at this specific time, when it's at this horizontal position, so when it's 70 meters away from its initial point of projection, it's at a time of 2.88 seconds, and at this time, it is at a height of 10.14. And because this is greater than the 10-meter vertical wall, it means that the ball will clear the horizontal wall. So we're just going to make a little statement at the end. So as h is greater than 10, the ball will clear the wall. Now, all the information I went through in this video about the only force acting on the plane being the gravity force, and how to get these, like how to get the acceleration, the velocity, initial velocity, and position vector, all this can be found under the projectile motion subheading in the textbook, which I've got over here as well. So that's how you